Now we will see about logical statements. Logical statements are the statement which gives answers in 0 or 1, true or false. It is also called as declarative sentence or propositional logical statements. These statements can be either true or false, but not both. Logical connectives are used to represent the logical statement, such as and, or, not, if, and then. These are used in logical statements. Now we will see that what are the connective symbols used in these logical statements. There are mainly 5 connective symbols which are used. This is called as and it is used in conjunction. What is the example of the and? A and B. Next is or. This is how or is represented. It is also called as disjunction. This is how it is represented. Next is implies. Implies is also called as implication. This is how implication is represented. Next is if and only if. It is also called as biconditional. A biconditional B. Next is not. This is how not is represented. It is also called as negation. This is how negation is represented. Now we will see truth tables based on the connective symbols previously discussed. First is conjunction. That means and. In this table, we can see that if both the statements are true, the answer of the conjunction is true. If one of the statement is false, the answer is the false. Next is disjunction. That means or. In this truth table, we can see that if both the statements are false, then and then only the answer is false for the disjunction. Otherwise, if any of the statement is true, the answer will be true. Next is implication. Implication is represented as either this or this way. What we can do with this, if A, then B. The truth table of implication is given like this. If both the statements are true, the answer of the implication of the two statements is true. If first statement is true and the second statement is false, A implies B is false. If first statement is false and the second statement is true, the implication of A and B is both the statements are false. The implication of A and B is. What we can say from this implication table? If first statement is true and second statement is false, then and then only the implication of both the statement is false. Otherwise, for all other cases, the answer will be true. Let's see one example. If an apple is not green means false statement. Then it must be red, means true statement. What we can say from this is whole the sentence is true or not. If we think, then we can say that it is the true statement. Why? Because if apple is not green, then it must be red. So, from the truth table of implication, we can say that if first statement is false and other statement is true, the answer will be. So, this statement is. Now, what is biconditional? The truth table of biconditional is given right there. In this truth table of biconditional, if both the statements are true or both the statements are false, then the biconditional answer of the true statement is true. Otherwise, it will be false. The last truth table is of negation. Negation is negative. This is how it is represented as. If the statement is true, the negation of that statement is false. If the statement is false, the negation of that statement is. Now we will see about the relations. But before we understand what is relation, we have to understand two concepts, natural numbers and integer numbers. What are natural numbers? Natural numbers start from 1 and goes up to infinity or n. What is integer numbers? Integer numbers are start from minus infinity and goes up to plus infinity. Means it contains 0 and minus numbers also. Now the question is 0 is either even or odd. And the answer is 0 is an even number. The concept of relation. For this, we have taken the set A, 1, 2 and 3. Based on this set A, we have taken A cross A. A cross A means Cartesian product of the given set. We have also taken one another set X, which contains D, E and F. From this set, we have taken relation with X, relation with Y and relation with Z. Relation with X, that means Rx comes from this set, Ry comes from also this set and Rz comes from this set. Based on this example, we will understand each relation. Now we will understand each relation. There are 6 mainly relations which we will understand from this. First is reflexive. What is reflexive? Every element is related to itself. That means reflexive relation. Now we will see one example so you can understand what is reflexive relation. For the set A, which contains 1, 2 and 3, what we can say that is it reflexive or not? For that, we have to take the Cartesian product of the set A. For every element of set A, the pair of the element, that means A, comma A, is belongs to relation R. Now we will see in this example. The Cartesian product contains 1, 1, 2, 2, 3, 3, 1, 2, 2, 1 like this. If 1 is inside the set A, the pair with itself should be inside the relation A. Is it true? Yes. If 2 is inside the A, the pair with itself element should be inside the A. True. So we can say that the Cartesian product of A is, that is A cross A is reflexive relation. Next is irreflexive relation. Irreflexive is the opposite of reflexive. No element is related to itself. That means if any element A is from set A, then the pair of with itself does not belong to relation R. For example, if 1 is inside the A cross A, the pair with itself element should not be inside the relation. So here Cartesian product A cross A is not irreflexive. It is reflexive. Then what is the irreflexive example? Examples such as 1, 2, where 2, 1 is not, where itself the element is not inside the set. The example is 1, 2, 2, 1, 1, 3, 3, 1, 2, 3, and 3, 2 is the irreflexive relation. Next is symmetric. Symmetric means if the element A and B comes from the set A, that means if A, B belongs to R, then the pair, reverse the pair. B, A should be come from relation R. Here the example of symmetric is Cartesian product A cross A. How we can say that if AB belongs to R, then BA belongs to R? See, 1 1 is belongs to R, then reverse of 1 1 is 1 1. This is how 2 2 and 3 3 works. Now the next is 1 2. If 1 2 is belongs to R, that means relation A cross A, then reverse of this 2 1 should be belongs to A cross A, which is true here. Now 1 3, then 3 1 is also there. 2 3, then 3 2 is also there. That means A cross A can be symmetric. But next is asymmetric. Here, if AB belongs to R, then BA does not belong to R. The opposite of symmetric is asymmetric. Here, we have taken one more example of set X, DEF, where we have taken Rx, Ry, and Rz. In this, we can see that Rz set is the asymmetric. Why? Here, DE is the part of the set Rz, but ED is not. Here EF is the part of RZ, but FE is not. So this relation RZ is called as asymmetric. Now we will see antisymmetric. If AB belongs to A, and that means AB belongs to R and BA belongs to R, then A equal to B. Here in this, we can see that Rx is the example of antisymmetric. Why? If DD belongs to R, reverse of DD is DD, then D is equal to D. Same for EEFF. Like this. Here D comma E, but there is does not here D comma E is there, but reverse of this ED is not present. So we can say that it is antisymmetric. For EF also, FE is not present. DF, FE is not present. So we can say that it is antisymmetric. Now we will see the last relation, transitive. For the pair AB belongs to R and BC belongs to R, we can say that the first element of first pair and the second element of second pair should be from relation R. Then this relation can be called as transitive. In this example, in the right side, the relation RY is called as transitive. Why? We can see that DE is belongs to RY and EF, that means the second element should be same, EF should be in the RY, which is there. So if DE is belongs to RY and EF belongs to RY, then the first element of the first set DE, that is D, and the second element from the set F should be in the set RY. That means D and F should be in the relation RY, which is there, DF. So we can see that the RY relation is the transitive relation.